Getting a visual representation of atomic excitement and photon emission has been really helpful for my students. So to summarize what they're seeing, I'll give them this note, and they've found this useful in physics, and it has even helped them with their senior chemistry courses as well. So I will start by actually showing them the emission spectrum of hydrogen using the spectrum tube. This I find is really great for them to see in real life, but when we were online, I did show them just the visual picture of it. So we talk about atoms in excited state. They've seen this before.
Atoms are in an excited state when one or more of the electrons is in a higher orbit than their ground state.
And we'll review what that means to be in the ground state. If we're using this as our model of the atom, which I know isn't perfect, but it's a pretty good analogy for what's happening, then here in the nucleus we would have one proton, and then the electron that's here would be in the ground state. So I would have them label that. And then we're talking about excited states. So an electron can be in an excited state if it's in a higher orbital. So here it could be in the second, the third, the fourth, the fifth, the sixth, etc. We only have that one electron if it's just hydrogen, but these would be different excited states that can occur at different energies, but we'll get into that. So those would be the excited states. And then I would also label for them the different numbers here. So this would be the first shell, and then the second, third, up to the sixth. So this is relating their physics to their chemistry knowledge, and then so far this should be pretty good. The electron shells exist at certain distances for each element. So for this one, we're just looking at hydrogen. And when an electron is in an excited state, it has additional energy.
Consider the analogy of the atom, with its electron shells being like a pit, with the nucleus at the bottom. The electrons are like climbers in the pit. In order to go higher, they need to gain energy. Electrons gain energy when they absorb photons of light. Absorbing a higher energy photon results in the electron moving into higher electron shells.
So then we'll go through and talk about what that looks like in the atom. So down here we have the nucleus, and then we have these different orbital shells, labeling them the same as they are above. And then asking the students to visualize these shells as being different levels of a pit, or you can think of this as stories in a building, whatever you think your students will respond to. So in order for an electron to move up from its ground state, it needs to absorb energy. So depending on the amount of energy, if it absorbs a certain amount, it can move up to the second orbital, or if it absorbs more, it can move up to the third, the fourth, the fifth, the sixth, etc. And there are different energy levels that it can absorb that relate, later we'll see, to the colors of light that it emits. I'm going to focus on this second orbital because it will relate exactly to what the students see in the Balmer lines or in the emission spectrum of hydrogen. So then I'll get into actually coloring the visible portion of light with them. And when I do this, I have those delineations, but I always color over them to kind of blend the colors better. So students will recall the visible spectrum. We've got violet, blue, this here is cyan. That comes in handy when using the emission spectrum of different elements. Green, yellow, orange, and red, and that should be familiar to them. Then we'll start talking about the photon emission.
Photons are fundamental particles that transmit light. When an electron drops from a higher orbit down to a lower orbit, it emits a photon. The photon has the energy that is equal to the energy quote-unquote lost when the electron drops to a lower orbit. The frequency of the photon depends on the energy that is quote-unquote lost. This is given by this equation, which involves the energy emitted being equal to Planck's constant multiplied by the frequency. The frequency also occurs in the universal wave equation, which also includes the speed of light and the wavelength. The emission spectrum shows the bright lines of color relating to the photons released when an excited atom's electron drops shells. We saw 4 different color of lines in hydrogen's emission spectrum, 2 in the purple, 1 in the blue, and 1 in the red.
So where do these lines come from? These lines come from electrons that had been excited by the electricity passing through the hydrogen gas in the spectrum tube that then dropped down back to a lower state. In this case, it wasn't actually their ground state. It wasn't going from n equals 2 down to n is equal to 1. Based off of the frequency and energy of the light, that energy that was absorbed by the electrons to bring them into a higher state and then is then emitted as the electrons drop down, don't drop down to their ground state. Instead, these are dropping down to n is equal to 2, still an excited state, but they do emit light that we can see. There are emission bands in the infrared in this section and in the ultraviolet, but I don't include those with my students because they cannot see them. I mention them, but they can't see those lines, so I don't really get into that as much. And that's why I'm focusing mostly here on n is equal to 2. I'll highlight that up here. I also make a point for my students to make the shape a little bit different. But what they're seeing when they see those emission spectrum for hydrogen is they're seeing electrons from higher orbitals dropping down to n is equal to 2. So the electricity passed through and brought electrons up to the 6th orbital, or the 5th orbital, the 4th, the 3rd. And when these electrons now drop down to the 2nd orbital, they're going to emit a certain amount of energy. The amount of energy emitted when the electrons drop down to the 2nd shell is dependent on this equation. It's equal to the amount of energy they absorbed when the electric current passed through. So when this electron drops down from the 6th down to the 2nd, a lot of energy is given off. In fact, the amount of energy that's given off is 48.4 attojoules. Now, atto is not a common prefix that we use often, but it means times 10 to the negative 18. So attojoules, very, very small number. But when you use this equation here, you can determine what is the frequency of a photon that has 48.4 attojoules. That 48.4 attojoules is a really small amount. We can use this equation to determine what is the frequency of that emitted photon. So here we'll start with 48.4 exponent negative 18. That's the attojoules part. We're going to divide that by Planck's constant, which is really, really small. And then we get here 7.30 times 10 to the 16th power. Well, that corresponds to 730 terahertz in terms of frequency. So this band of light here is related to, is actually caused by an electron in the 6th shell, or going down from the 6th distance down to the 2nd. And you can repeat that for all of the other colors of light.
I would provide the energy for the students and show the calculation that determines what frequency of light is emitted, and then show how that directly connects to the color of light that we see in the emission spectrum.
So in order for an electron in this 2nd orbital to move up to the 3rd, it would need to absorb 30.3 attojoules of energy. And when it drops down, it releases that 30.3 attajoules of energy as red light. The same goes for these other variations of excited electrons depending on how much energy absorbed. That's equal to how much energy they emit. And this is a great way to connect that hydrogen emission spectrum to what students will actually see in their physics and chemistry courses.